Welcome back. So last time we talked about AC circuits. We'll be continuing in this topic today. So quickly, we talk about the for AC sources, instead of direct current or voltage, you get as your sinusoidal for voltage or current. So either way, okay. So V then could be a sine function or cosine function. And that's as a function of omega t, omega is 2 pi times F. For resistors in AC circuit, so the current and voltage are in phase, they peak at the same time, so they are called in phase. And because for AC signals, you have sine or cosine function for voltage and current, so then they will zero out to be, or average out to be zero. So then another term called root mean square quantities are used to describe the voltage or current, okay? So for the resistor in AC circuit, the power consumed is equal to then the root mean square current square times R, or root mean square voltage square over R, or root mean square of voltage times root mean square of the current. So basically the similar expression as you would have for the DC circuit, but just using the root mean square quantities for voltage and current, okay? Inductors in the resistor, then if voltage is a sine function, then current will be a cosine function. So they do not peak at the same time. Actually, the voltage leads by 90 degrees. That means the voltage peaks first and then current peaks later. So the response of the inductor to the voltage applied, this is called reactance, inductive reactance, is equal to omega, which is 2 pi times F times L, the inductance, okay? The average power by the inductor in the AC circuit is going to be 0, so it doesn't consume any power. For the capacitor in the AC circuit, so current is, if voltage is sine function, current then is a sine function plus 2 pi or cosine function. Okay, so you do derivative of the V to get the voltage, okay, or dQ over dt, which Q is related to V in that sense. Okay, so again, the voltage and current on the capacitor, they do not peak at the same time. In fact, the current leads by 90 degrees in this case, okay? The reactance of the capacitor is called capacitive reactance, is equal to inverse of omega times C. In the previous case for inductor is omega times L. So in this case it's 1 over omega times C. The power on the capacitor average out to be 0. Okay, so then it doesn't consume any power in the circuit. We also talk about phasor. So phasor is a quantity we use to visualize the phase relationship between the voltage and current. Okay, so for the voltage phasor, so this is the maximum. So that at any given time moment, the voltage on the particular element is the y projection of this phasor, or similarly for the current phasor. So current phasor is in this direction, then the current at any given time for the element is y projection of this, okay? So this figure is for then a resistor. So for a resistor, the voltage phasor and then the current phasor, they are in phase, so they have at the same time, so directional angle is the same, okay? For a capacitor, so then the current leads 90 degrees, so that means this vector and then the voltage phasor, they are the angle between the two is 90 degrees with this current phasor is leading, okay? So current phasor goes counterclockwise direction, and then this also follows that by 90 degrees at any given moment. So if you have a RC circuit in the AC signal or AC circuit, then the current, overall current should be the same because they are in series. So this is the current phasor for the whole circuit, and the green one. So then the voltage phasor on the resistor will be this guy because voltage is equal to current times R. the current voltage phasor for the capacitor will be this guy. Okay, so then overall voltage phasor for the whole circuit will be this vector plus this vector. So then it's this guy. Okay, so from the vector addition, graphically, you can see that. So you move this guy parallel over, then the resultant will be this one. Okay, so vector addition, then in this case, you'll be doing the kind of Pythagorean theorem because these two are perpendicular to each other. Okay, so it turns out to be maximum voltage phasor for the whole circuit is equal to I max square root of R square plus XC square. So square root of R square plus XC square, then we call it as impedance of the whole circuit. Okay, so it's combination of reactance and then the resistor. Okay, so that's called impedance. And we also look at the power factor, so which cosine phi is equal to basically R over Z, that is called the power factor because that's how much the power is consumed in the circuit. So it's equal to I squared times R because the capacitor in the circuit doesn't consume any power. So then overall power on the circuit will be just based on the resistor, okay? And then it turns out to be R over Z. All right, so then let's take a look on the we have an RL circuit. So if we have an inductor and resistor in series to each other. So similarly, then in this case, the whole circuit will have impedance equal to R squared plus XL squared. Okay, so this is in analog to the capacitor in this case. And then for inductor, this is omega times L, so that to be squared. So the blue, this is the voltage phasor for the inductor, okay? And for the resistor would be this guy, the yellow one, okay? The whole circuit would have I max as the green here. So overall voltage phasor for the whole circuit should be this guy, the blue vector plus the yellow vector. So again, it will be this guy. So they again is in the diagonal line of this rectangular shape, okay? So then it will be, again, this the kind of Pythagorean theorem. So in that case, okay, so the Z here, the impedance for the whole thing. So V max equal to I max times Z for this guy. It's going to be equal to I times Z or I max times Z, which Z is impedance, okay? Power factor now, again, on this case, because inductor will consume zero power, so it's only all on the resistor, so it will also turn out to be just R equal to R divided by Z. Okay, so power factor for the circuit will be cosine phi R over Z, and then the phi is related to the angle here between the maximum or the overall voltage phasor and then the overall current phasor. So if you are wondering why that particular cosine of phi and then what phi the angle will be, okay, so that's the angle. All right, so for resistor only, so then if you only have resistor in the circuit, so then this will be just a flattened line equal to 1. For if you have an RC circuit, okay, so it depends on the frequency of the signal. The RC circuit, the cosine of phi will be equal to R over Z, and then in the Z, down there will be R squared plus 1 over omega L, okay? So when omega is equal to 0, so 1 over 0 will be very large. Okay, so then it start out at 0 because everything in the denominator will be very large. So which is this guy here. Okay, so when this is 0, everything is very large. So Z will be infinity. Okay, so then becomes 0 here to start with. Now for inductor LC circuit, it start with the maximum when omega equal to 0. So then this is 0 here. So be equal to 1 starting from 1 and then decreases out. Okay. So for RC circuit, its frequency is very high, then it's approximately equal to just a resistor. So then in that case, the capacitor just becomes a straight wire in that sense, okay? On the other way around, for RL circuit, if you have inductor in the circuit, when frequency is very low, close to 0, then it becomes a straight wire in the circuit. But as frequency goes up, then its reactance will be very big, okay? So then the impedance for the whole circuit will be very big. All right, let's take a look on this one. So it says, the RMS current in a RL circuit is 0.26. So IRMS 0.26 amp. It's connected to an AC generator which has a frequency f 60.0 Hertz. Okay. And RMS voltage VRMS is equal to 25 volts. Given that the inductor has a inductance of L equal to 145 10 to the minus 3 millihenry minus 3. What's the resistance of resistor? So what's R? What's R? So this is the RL circuit, okay? So we know that V max, right, equal to I max times Z. So similarly, VRMS, if you're looking for VRMS, then it's IRMS times Z, okay? So we can calculate Z in this case then, and then Z is for RL circuit will be square root of R squared plus omega L squared, right? So then we can calculate this guy given the frequency, so omega can be calculated, okay? So first, let's calculate the I, which is going to be, or actually Z. So Z is going to be equal to VRMS over IRMS, okay? So for Z, that is VRMS over IRMS, 25 volts over 0.26 amps. So that gives you 96.15 in ohms, okay? Now this is can be also written as that. So then we are going to set up that 96.15 ohms, right, equals to square root of R squared, which is what we are looking for. So actually, given that, yeah, right. So R squared plus omega will be 2 pi times frequency 60 Hertz, and then times the inductance 145 times 10 to the minus 3 Henry, and to be squared, okay? So then we'll square the both side equation, right? So let's go here. 96.15 to be squared. So let's just skip the units for now and then have everything else in SI unit, okay? So plus 2 pi times 60 times 145 10 to the minus 3, okay? And then that to be squared. So solve for R, okay? So I think you guys know how to do that. We'll just skip that. So this guy gives you 79.1 ohms, okay? For the resistance, okay? So part A. Part B is asked find the RMS voltage across the resistor, okay? So once we have that, so then for B, V RMS on the resistor should be just equal to the I RMS times R, okay? So 0.26 amps times that 79.1 ohms, okay? So that gives you about 20.6 volts, okay? Now C, find the RMS across inductor. So VRMS on the inductor, RMS on the inductor, then will be IRMS, okay, times XL. So 0.26 again, XL is 2 pi F, okay, and times L, okay. So this is about 14.2 volts, okay. And D says, use your result from B and C to show that square root of this guy square plus this guy square is equal to 25. Okay, so basically, if you see these two, right, these two add up to be 34.8, okay, which is higher than 25, but we cannot just add them algebraically, right, because they are phasors, right? So we have to do vector form. So in this case, these two are perpendicular to each other, so you are doing the scores add up, okay, MSL and then score. So that's going to be 20.6 square plus 14.2 square. Okay, so it turns out to be 25 volts, okay, which is in agreement, okay, with the overall voltage, RMS voltage. Okay. All right, let's go back to the PowerPoint slide. So we have looked at RC circuit and then RL circuit under AC signal. Now let's put them all in just one circuit, right? So RLC circuit, that in a single circuit, we have all of them. So then on the capacitor, right, we'll have I maximum leading is V max, okay? And then on this guy, we'll actually have the voltage leading the current. Okay, so the currents to all three should be the same. The green one, but then this guy, the V max will be I max times R. Okay, so it will be this one. So at the end, for the maximum voltage for the whole circuit, for the RLC circuit, right? So you are doing vector addition of this, the red plus the yellow plus the blue together, right? So these two are in opposite directions. So then you do XL minus XC or either way around because you square it for the impedance, so it doesn't matter. And then this one for the inductor, for the capacitor. Okay, so then this one square, so this one minus that guy will become this one. Okay, the purple. So then diagonal lines of this purple and this guy, okay, makes this rectangular. Okay, so square root of R squared plus XL minus XC. Okay, so you don't do XL plus XC because those two are always in the opposite direction in the RLC circuit. Okay, so then it turns out to be square root of R squared plus omega L minus 1 over omega C for the Z, for the impedance. Okay, so once you have the impedance, then you can calculate the V RMS or IRMS given like which one is given, and then you're looking for the other quantity. Okay. All right. So in this case, the phase angle, okay, if you look at the phase angle here, this phi, then it's related to you can do this over that. So this tangent phi is equal to this guy over that. So it's the XL minus XC divided by R. Okay. In that sense. In the case of XL equal to XC, then the phase angle will be 0. Okay, so then everything will be just simplified as the just a R in the circuit. Okay, so because XL and XC will then cancel out in that sense. So power factor again will be equal to R over Z. So depending on what Z you have. So for this circuit, that's the power factor again. So you need to find Z first. Okay. All right. Let's take a look on this one. So it says you have an RLC circuit. R is 8.8 kilo, C is 0.12 microfarad, and L is 28 millihenry. The generator supplies an RMS voltage 115 at a frequency of 60 Hertz. Okay, so you're given those quantities. So RLC circuit, AC circuit, okay, AC circuit. Frequency 60, VRMS 115 volts. Yeah, and then R equal to 8.8, 10 to the third. C equal to 0.12, 10 to the minus 6. L equal to 28 times 10 to the minus 3 Henry. Okay, so find RMS on each of them. So that means you're looking for VRMS on R, which should be IRMS times R. Okay, so we just need to find IRMS, and then similarly VRMS for L. So will be just equal to IRMS times XL. And then VRMS on the capacitor should be IRMS times XC. Okay, so R is given, XL, XC can be calculated. Okay, so we can calculate then one by one. I think the first thing to do, we can calculate is XL. XL is 2 pi FL, right? So 2 pi 60 Hertz, F 2 pi F, L is 28 times 10 to the minus 3 H. Okay, so that will give you 10.6 ohms. XC 1 over 2 pi FC. Okay, so 1 over 2 pi 60 and then 0.12 10 to the minus 6. Okay, so everything together. And that will give you 22.1 kilo. 22.1 times 10 to the third ohms. Okay. So then with that, we can calculate Z for the whole thing, square root of R squared plus XL minus XC squared. Okay. So 8.8 10 to the third squared plus 10.6 minus 22.1 10 to the third and square root. Okay. So this Z is equal to 23.8 kilo ohms. And once we have that, we can calculate for the IRMS, because IRMS will be just equal to VRMS over Z. Okay, 115 volts divided by 23.8 10 to the third ohms. So that gives you 4.83 10 to the minus 3 amp. Okay, so then this one goes in there. For your VRMS on R, it's going to be I RMS 4.83 10 to the minus 3. Okay, amps times 8.8 10 to the third ohms. So that will be 42.5 volts. Okay, on the first one. On the second one, VRMS on L will be IRMS times XL, that guy 10.6. So then that gives you 51.2 10 to the minus 3 volts. Okay. On the capacitor, again, IRMS times XC will be that guy, 22.1 10 to the third ohms. So that gives you 106.8 volts. Okay. So again, if you look at them individually, if you add them up, that goes to about 150, which is larger than 1.5. Okay, but we shouldn't do that, right? We should do for the VRMS total. So then for RL circuit, it should be just VRMS on R squared plus. Okay, now for these two, you don't add them up, but you do the difference of the two because they are opposite to each other direction wise. Okay, so square root of 42.5 squared plus 51.2 10 to the minus 3 minus 106.8 and squared. Okay, and this will turn out to be exactly 115 volts. Okay, so it's always worthwhile to check at the end if your total RMFs will be according to what you have, 115. All right, so going back to the slide. Then overall, the power in the AC circuit, if you have capacitor, resistor, and inductor in the circuit, right? So everything would, for inductor and capacitor, they do not consume any power. So again, it will be on the resistor. So IRMS times R, or square IRMS square times R. Okay, so it turns out to be, again, IRMS times VRMS times R, and then P average will be equal to I RMS VRMS cosine of phi, where cosine of phi is equal to R over Z. Okay, so this is the power factor for the AC circuit. So doesn't matter if you have RC circuit, RLC circuit, or RLC circuit. They are power factor is all cosine phi, and then it's R over Z. Okay. So if we have a RL circuit, then or RLC circuit, so then in the impedance, we know that it's equal to R squared plus XL minus XC squared, right? So the current RMS current is V, then divided by Z in that case. Now, in the denominator here, you do see this has a minimum value when these two equal to 0, right? Or these two equal to each other, so they cancel out. So then it's only V over R, okay? So in that case, you get maximum RMS current, which is called resonance, okay? So for the resonance frequency of the RL circuit, then it'll have the condition of this guy equal to that guy. This will be then 2 pi F L times L, and then XC will be 1 over 2 pi F times L, okay? So for the resonance frequency, we call it F sub naught. So then rearranging the terms, you'll get F sub naught to be square root of 1 over 2 pi times square root of L times C. Okay, so that gives you the resonance frequency then for the circuit. So it depends on then the resistance. If you have larger resistance at resonance frequency, you get smaller current. If you have smaller resistance, you get larger resonant current, or the IRMS current, okay, at resonance frequency. Okay. The last one here, it's about transformers. So in reality, electric power plants, so this is a European configuration, one of them, to produce a relative high voltage, but not as large as the voltage in the high power transmission. Okay, so in the high power transmission, you need a high voltage because then in that case, the current will be smaller because the power output of the power plant is fixed. Okay, so power output here is equal to a constant numbers throughout. So then when you have higher voltage, you have smaller current. Okay, small current in the wire that result in smaller power dissipation to the environment. So power equal to I squared times R, okay, in that case. But changing voltage of the electricity from a lower value to a higher value, we then need to use a step-up transformer. And then changing the voltage from high to low, we use a step-down transformer, okay? So in that sense. So basically a transformer is something like this. So this is in the iron core here, so which is a ferromagnetic material that will carry the magnetic field or magnetic flux here. So you have turns of coils in the primary here called MP, and then voltage on the primary coil called VP. Secondary coil, we have different number of turns of coil there, and then voltage, it's called V sub S, okay? For a step-up motor, you'll have less coils on this side, and then more coil on this side. For a step-down motor, you have more coils on the primary side, and then less coils on the other side, the secondary, okay? Because the flux through each of the coils here is the same as the flux of each of the coils here. So then it really depends on how many turns of coils you have on either side, right? So more turns on one side, that means the voltage on that side will be more because voltage is related to the induced voltage of the flux through your coil, right? Faraday's law here comes into play. All right. So exactly for the secondary coil voltage, it's minus NS delta phi over delta T. This is flux through each coil. And then primary is minus MP delta phi over delta T, okay? So you can rewrite these two equations. So just put delta phi over delta T to one side of the equation because change of flux through each coil is the same on both sides. And so that should give you the same on the other side. So delta phi over delta T on this one is equal to minus Vs over Ns, right? Delta phi over delta T on this equation is equal to minus Vp over Np. So then Vs over Ns is equal to Vp over Np, which means the voltages in the primary and secondary, their proportional to their tensor coils. Okay, so this is then the transformer equation. V sub S over Vp is equal to Ns over Np. And also have currents involved in the equation, because Is times Vs should be equal to Ip times Vp. Okay, so more cross multiplication in there, because power input should be equal to power output, okay, in the circuit, in the primary coil and in the secondary coil. So basically you are just transforming power from one side to the other side, okay. So that's a coil dust, right? Inductor, right? It's just not consuming energy, but storing energy and then storage energy, and then make use of that to the other part of the circuit, okay. So then current in the two circuits is proportional to their turns of coil, okay. So you have more turns, you have less current. You have less coils, you have more current, okay. All right, so the last example for the day here, so it talks about the electric motor in a toy train that requires a voltage of 4.5. Find the ratios of the turns on the primary coil to the turns of coils on the secondary. Okay, so given that you want to step 120 volts household voltage to a 4.5 voltage. Okay, so basically what happens here is the primary circuit has Vp equal to 120, and then you want to step it down to 4.5. You will use the transformer, right? So transformer equation says Vs over Vp over Vs is Np over Ns. Voltage are proportional to their turns of coils. And you are looking for the ratio Np over Ns, right? So Np over Ns then will be simply 120 over 4.5 volts, which is 26.7, about that, okay? All right. So we'll stop there, and that conclude this chapter, and then we'll come back next time, okay? See you guys. Bye.